One, two, three, four, 5, 6, 7. Okay, yeah. Mystery solved. Much easier than usual. I just forgot to turn my microphone on. Okay. So let me try again. Welcome everyone to Randomness, a show where we, as usual, look at how this awesome database Tagemittal is built, how it works inside, and really what we are learning is not so much how Tagemittal in particular works, but in general, how to build your own distributed systems, your own storage engines, your own simulation testing frameworks, because the most exciting thing about Tagemittal is that it is super simple, it doesn't have dependencies, and although the code base is not tiny, it is like, it's not a giant stack of dependencies, so if you just have certain amount of perseverance, you can just start reading it from main and understand everything there is to building a modern distributed database for financial accounting. Okay, so what are we going to talk about today? Today we are finally diving really deep inside the VOPR, our view stamp replication, deterministic simulation testing harness. This is the magic which allows us to keep Tagemittal as reliable as it is. And so far, we've been talking about VOPR a lot, and I think we've even debugged, I don't know, I think at least 3 VOPR failures live. One is like the other week or something like that. And we even learned how to run the thing, but we haven't learned how the thing works. So today we are going to start our deep dive into the implementation of our test harness. Okay, so let's look at our hunters in the snow and go to Randomness folder and okay. let's start VOPR, and okay, this definitely shouldn't be a lol. Okay, so as a reminder, what if then last time we learned that hey, you could run VOPR like this. So this will run VOPR pass and seed number 92, and I guess today we'll start just from main and learn how exactly that works. Okay, yeah, so you see, it works. Hopefully this wouldn't be bug. Okay, it is not a bug. Okay, so let's start. This is our main in VOPR.zig. The first thing we do here is that we set up a buffered writer for our logs, and that's actually interesting because I think the default behavior on Linux is that your standard output is either buffered or line buffered. So basically, like, if you print just a little bit twist it out, it won't actually immediately go there, and instead will like line turn buffer. But standard error is unbuffered. Whenever you write in something to standard error, it is immediately a syscall, it immediately goes into the kernel, it immediately goes to your screen, which is usually good because, like, standard error is, well, it is an error. You want to see that output. But inside deterministic simulation testing, you are actually going to see a lot of errors introduced by fault injection. So like literally, it's like a typical VOPR run with logs enable like produces gigabytes of logs. Actually, okay. Why don't we just say it? So we compile this with release, and we say that we want full log, and we redirect this to log.vopr, and we'll see how much it is. But it's going to be multiple gigabytes. So just like writing all that stuff takes a lot of time, and that's why it is like actually crucial to set up a relatively fast logger. Okay, then. Use SD testing allocator when all dnit leaks are fixed. I think we shouldn't. We shouldn't have any dnit leaks left at this point. Actually, okay. So this is surprising. Okay. Let's see. Actually, okay, yeah. So this was a surprisingly tame run. Okay. Is it even everything? Okay. Well, yeah. Okay. It is everything, but okay. How could it? Okay, I don't believe it. Like, why it's just like 61 max? It feels incorrect. Feels like it should have been much larger. Well, okay, maybe we've lucked out into a very small run. Anyway, well, there is actually this is more responsive. So, like in general, in Tiger we allocate memory at the startup. We never ever allocate it, so we don't care about our allocator at all. So, like you see, like in VOPR, we just use like page allocator. So like any allocation is backed by a page, and we just like don't care about this at all. But we probably do want to like be proper Zig programmers and ensure that we dnit everything. So let's actually try just an allocator. Like, will it work? I think it should. But maybe it won't. Or can it be the case that, okay, cannot use testing allocator outside of test block? Okay, let's actually, okay, okay. So, sorry, folks, but I'm bored, bored here. So let's fix this. I think we should just go and fix it right away, because I mean we shouldn't have to do this. Branch fix VOPR allocator. Okay, so let's go to the branch, and let's do more stream friendly. Theme. Okay. So like here. So I think what I want to do is this. I want to say that we have allocator instance, which is std heap a general purpose allocator, and then I want to say that actually I don't want to call this allocator. I want to call this GPA, general purpose allocator, because you should mention which one it is. Allocator. Okay. And then I also want to check that there is no leaks here. Okay. Okay, then let's say that we are passing GPA here. Okay. Why do we need GPA here? This feels. Why do we need this? Shouldn't be passing the allocator. Like it doesn't make sense. Okay. Sorry, I lost myself. So class recoverable. Class recoverable needs allocator, which we pass to for missing prepare, which we use. Where do we use this? I mean, okay. Okay, so we should be pre-allocating this actually. Oh, okay, but okay. Anyway, and that's kind of like besides the point. But we do want to. We do want to fix our typos while we are at it. Okay, so let's see. Let's see now if that works. Okay, seems working so far, but we've leaked some memory. Okay, should we chase this? Should we chase this? Okay, let's chase this. Because actually I haven't used leak checking features of Zig's allocator, so I'm actually curious before. So I'm actually curious how does that works, because I think there should be some way to figure out what's leaked. Okay, so let's see what's in that leak. Okay, so it just doesn't. detect leaks. Okay. I wonder if we say detect leaks, will it actually print something useful? Oh, I think there should be some configuration which asks us to record stack whenever we are allocating. Okay. Okay, so presumably it just does okay, well. Okay, so I'm not seeing this. Oh, I think I know it. Or maybe I don't know. Okay, so 8 logs, just not error, and the log is okay. From GPA, so in our VOPR, we have log override function, and we should say or scope. So yeah, I think someone just ate. Well, our log override just ate our logs. Okay, so I wonder. Ah, okay, perfect. Query intersections in auditor. Okay, this is the thing, and like a little bit of trivia. Like last week, I've learned that in English, whenever you have a U, like in audio, auditor, I don't know, auction, it actually is pronounced as O and not as a like AU, not an auditor. So yeah, that's a little bit of trivia. Okay, so query intersections. We allocate them, we free them. If we have an error, yeah, and of course we don't clear this up. Okay, so let's do manually the thing that Rust does for us, which is like write the init. And let's say let's also like order it in the reverse initialization order, which is idiomatic for us. Okay, in flight. Wouldn't it be great if there was some kind of static analysis to ensure that this happens? And I mean, like Rust does systematically with destructors, and I actually think I prefer seeing explicit deinitialization code in the source code. Like it doesn't bother that I have to write this that I have to write this init function. It doesn't bother like there's like a little bit more typing that you like need to do defer. What does bother me though is that if you forget one, you don't get an error. So like I guess in my ideal language you would pretty much like in Zeek spell those explicitly, but you would also have some kind of static check to require you to you should use it. Okay, payment transfers. Expiry payment transfers. Okay, then we have query intersections. I think this is also self-query intersections. Then accounts state, and last of all, accounts. Okay, hopefully this leak is fixed, but it is not clear if everything is fixed. And while we are at it, let's rename allocator. Well, let's rename allocator into GPA into a separate commit. VOPR fix memory leak. VOPR idiomatic allocator name. Actually, I think I want to rename it to the GPA here as well. And yeah, this one should remain allocator. Okay, well, let's see if I haven't broken anything. Okay, seems fine. So here. Okay, yeah. So let's do this. I know that in the VOPR we also... Okay. So I do want to run VOPR in release, but I kind of like want safety checks. Okay, safety checks is going to be true, because even in really safe, we are running really safe. Okay, so that means that we can do something like this. Well, but we probably want differences. Okay. Okay, so we've managed to read the first two lines of VOPR. Let's get to the third line. Okay. Parsing command line arguments. That is our standard tiny library for arg parsing, which I think we probably should cover at some later point. Okay, so let's add a note about that. Well, I don't want to open directory. I want to open to do and actually, okay, snap test.zik and well, and copy how.zik. Okay. Sadly, yeah. Sadly, I create more topics for discussion than I'm able to cover. And okay, while we are doing this, let's also equals testing. So we support two-state machines in VOPR, like the account and test, and probably we'll even start with testing. And I want to check that neither of them leaks memory. Okay, so CLI arguments. CLI arguments are like relatively simple. So the only meaningful one is the seed. If the seed isn't passed, we generate random seed. If the seed is passed, we use that. Other than that, we have light mode, which disables some of the VOPR checks just in case that if you broke target really, really bad, then if your light mode fails, you'll get a simpler failure. And performance is, well, VOPR performance mode, which we should be able to cover, which we should really cover in a completely separate episode. And finally, like as we will see shortly, there is a boatload of configuration for a particular VOPR run, and we generate most of configuration at runtime without ability to actually configure it. So it is random, but for some most important ones, we do include tweaks here. Okay, at the same time, haha, our VOPR seems to be going strong. Okay, so let's actually submit a pull request while we are at it. Okay, and let's ask our CFO to also test this. Okay. Make sure that doesn't click map mode. There was no. And remove the best reviewed per commit. Well, actually, I mean, all of my pull requests are best reviewed per commit, but still, some are more better. Okay. Perfect. Let's get back to reading the code then. Okay. Like light and performance mode are mutually exclusive, and yeah, you see, like we don't support, like in our like CLI parsing library, like built-in exclusiveness checks, but I mean it's not really hard to add them all together. Okay, now this is with it. This it thing. There is one interesting tidbit here. So okay, so let's see what's going on here. First, we generate seed completely at random. Then we see if we have seed on the command line, and then we parse the seed. And parse seed function is actually pretty curious, because you would think it does just like parse and signed, but actually there is also a special case where you can pass a git commit hash as a seed to VOPR. So you could do something like this. Parse head. And we do this on CI. So on CI, we want to run like, smoke run a VOPR just to make sure that like, it compiles. But we don't really want to hardcore just a single seed on CI. But we don't want to take a seed completely random, because that will make reproducing the failure locally painful. So what we do instead is that we just use git hash as a seed. And it is kind of like git hash is random. Like, you push new commit, you get new hash. But at the same time, git hash is reproducible. So if CI fails and you rerun it, it is guaranteed to fail again. So it's kind of like not flaky. Okay. Then we create our pseudo-random generator, and that PRNG is going to generate every single random number directly or indirectly in this run. So this is like this is the single source of chaos. Like, you need a single source of truth in deterministic simulation testing, you need single source of chaos, so that if you like reproduce the source, you reproduce the result fully. And like PRNG is actually interesting. So in direction is the PRNG is actually interesting because like we used to just use std random, but I don't know, last week, 2 weeks ago, I've basically vetted it for 2 reasons. One reason is that PRNGs and standard libraries tend to change. They tend to become better, faster, stronger, but this would be harmful for us. Because for us, like, we don't want to, like, change our PRNG just when we update the version of a language, because we kind of like do want to change stuff only intentionally. Because I mean, we shouldn't rely on other of our PRNG, but we are humans. We could have a bug there, so we need a defense in depth against this kind of issue. And like our defense in depth is that like, hey, we kind of render just specific PRNG, and whenever we change it, we will know that we are only changing PRNG. So if something breaks, then we can confidently point at PRNG as the source of issue. And the other thing is that why we need our own PRNG is just to have like nicer API. And in particular, I really, well, let's see. Yeah, like we sometimes need to specify probabilities. And like, how would you specify probability? Well, you specify probability as a floating point number. But the problem with floating points is that like floating points are not 100% deterministic. Like they're like mostly deterministic on modern hardware, which follows IEEE 754. But even that, like, there are cases where there actually is no determinism. Like, for example, if you look at the WebAssembly specification, then it explicitly says that, hey, like, what not a number value you get out of certain operations is indeterminate. And we indeed have observed that, like, you get different behavior on like ARM chips versus x86 chips on like some WebAssembly runtimes. So like, if you want determinism, like better to stay away from floats. I mean, it is not mandatory. Like you could be deterministic with floats, but like, if you just don't have floats, then that's going to be nicer. So anyway, you can't use floats to specify probability. Well, the next idea is that you say, okay, I'm going to specify my probability as a percentage. So probability 20 means probability 20% means probability 0.2. But the thing is, like, for us, we sometimes need like ridiculously low probabilities. Like, like this probability is like 8 in 10 million. And like, kind of like it's not a percentage. You could implement like, percentage per milli per, actually, I mean, I don't even know what goes like after per milli in like this scientific terminology. So anyway, the nice thing is that like we actually want to specify ratios. We want to specify these like a replica pause probability. By the way, like, another case where it's like pause and like pause. So we want to specify these as a ratio because that's natural. But that means that you need to plug ratios into your PRNG so that you have like nice API. So how do we say this? Yeah. So we could say like, PRNG.chance, and then we pass a ratio. And yeah, that's just easier if you have your own PRNG. So you see like this ratio is like relatively simple. So we have denominator, numerator, and then we kind of like pick denominator -1 less than numerator. Well, hopefully it's will be all right. Well, actually, okay. So I mean, how do you test it? Like, you know, there's no off by one here. Well, I don't know, but this was my idea. So I just generated 1,000 examples, and with probability 2 out of 7, I kind of like increment balance. With probability 5 out of 7, I like decrement the balance. Okay, well, okay, no, it's different. So so I kind of like I decrement and increment with bias probability, and then decrement and increment again with bias probability, which is like it's not reciprocal. It is like, you know, they're complementary to one. And I expect that, hey, on average, it should be close to 0. And well, it is pretty close to 0. Well, actually, let's see if this is like 1,000. How far will we get? Okay. Build test chance. Let's see. Yeah, you see, like for like 100,000 tries, we strayed only by 100 from that probability. So that is probably correct. Although, okay. So now. Okay, yeah, so I was slightly suspicious that, like, you know, when we tried, what was it, 1,000, our balance was positive, and when we tried 100,000, our balance was also positive. So maybe there is a tiny bias to the positive direction. But no, like you see, we take 200,000 and the balance becomes negative. And by the way, I mean, like, this is snapshot testing. Like, people use snapshot tests. You are like, I mean, you should try to write a fast test, a property-based test, a randomized test. If you fail to write a randomized test, then, well, do snapshot test. Because it is really, really helpful to increase the pace of development. Okay. Let's see where we were. Okay, we were initializing our PRNG from C. Okay, now the interesting part, we generate a ton of options for our VOPR. So you see, like, this option struct is pretty large, and it includes other option structs which are also pretty large. So there's like a lot of things we can tweak here, and like significant part of configurations here are like probabilities. Like, you know, like, what is probability of a fault? What is probability of messages getting reordered in the network or something like that? And like, one major insight from the Fuzzen literature is that you don't actually want to fix the probability for your run. You want to select probabilities themselves randomly. This is like, well, kind of like, ideas in this area are called swarm testing. So, okay, let's see how we generate configuration for our VOPR. Okay, so we have up to replicas max replicas. We have up to standbys max standbys. As a reminder, standbys are nodes which do not participate in consensus, but which still get all the data out of the cluster. Okay, we have clients. We have configure for maximum batch size in this run. So this is so our messages are 1 meg, and 1 meg gives you like compile time limit on the size of the message. But if you allow messages to be full 1 megabyte long, then you need a lot of memory to manage it. I think we currently require like at least 6 gigabytes of RAM for running a Chagabel cluster. But sometimes you want to run Chagabel with fewer RAM. And the way you do it is that you set a runtime limit for the batch size, which is smaller than the compile time limit. And of course, you want to also fuzz against this batch size limit, and that is what we are doing here. Okay, limit for storage. Then, yeah. Cluster options, again, what I've mentioned, that we have 2 state machines. So state machine is compile time parameter, and it is either our real accounting state machine with full accounting logic, or a simple testing state machine, which is like key value store. Okay. So network options. Again, like what you would expect from the network. There is like count of nodes in our network, so replicas and clients, and then some configuration for how bad the network is. Again, and I emphasize, this is swarm testing. We kind of like, we don't set certain probability that a packet is lost. Rather, we pick probability at random. So in some runs, no packets are lost, and in some runs, a lot of packets are lost. So yeah, you see, kind of like, okay. So let's go one by one here. Okay, so one-way delay. So how many ticks it takes to receive a message? What is the probability of losing a single packet? What is the amount of packets that can be in flight between two nodes? Then our network also models so-called like clogged connections. So when a connection becomes clogged, that means that for a certain amount of time, it stops delivering messages and then delivers them in a burst. So again, to simulate a clock, you need to say how long the connection is going to be occupied, and also you need to say what is the probability that connection flips from being clogged to not being clogged. Okay, then network can duplicate messages with some probability, and finally network can partition the nodes, make it so that some nodes are unreachable from each other. Again, swarm testing. Rather than saying like, hey, this node is reachable, this node is reachable purely at random, which will get you a random partition, which might not necessarily be interesting. We first select a mode, like what kind of a partition we want. And yes, sometimes we want uniform partitions, but sometimes we want something similar, like we want to isolate exactly one node, or maybe we want to isolate n nodes. Okay, so this is partition mode. Then whether we partition symmetrically or non-symmetrically. So asymmetric partitions means that A can talk to B, but B cannot talk to A. Then again, probability to flip to partition, probability to flip from partition, and then for how many ticks a partition should persist. So there's like 3 parameters, like one state transition, second state transition, and what is like the minimal duration while the state is maintained. Okay, similar thing for reading from disk. I mean, kind of like network and disk are like basically the same. So what is our latencies? What is the probability of a fault? What is probability of misdirect? What is the probability of crash fault? So crash fault is interesting. So like these faults are more than like, normal faults where, well, actually like, abnormal faults where like, this genuinely fails. And to be honest, this happens like extremely rarely, but sometimes it does happen. So probabilities here are like very much inflated. But this one is interesting. So crash fault probability models the chance that a particular disk operation is applied incorrectly if the replica is failing at that moment. So like, you plug out power cable, or there is like, I don't know, some fire or something like that. So something which causes the process, the operating system, and maybe the entire machine shut down abruptly. And in this scenario, actually the probability of a fault can be pretty high. But still, again, we don't just set it to 80% or 90%. No, we say, hey, actually, sometimes it is, no. Okay, sorry for anyone who was blinded by a flash of white. Okay. We say, okay, sometimes we want crash fault to be like almost certain, 80%. And sometimes we actually want it to be 0. Okay, then, I mean, Tagabit can tolerate some faults, but it cannot tolerate all the faults. So if you just fault every single sector or every single disk, obviously the cluster will not survive. So we need some logic to figure out what we can fault and what we cannot fault. This is defined by the thing called fault atlas. So basically, what fault atlas does is that it tries to make sure that for every given sector on disk, there is at least one replica in the cluster where this sector is not corrupted. So it tries to prevent correlated faults. And like we kind of like want to say like how exactly are we spreading the faults. So for example, if our cluster contains only 1 or 2 replicas, apparently we actually prevent faulting a grid, which is okay. Yeah, that makes sense exactly. That makes sense exactly for the same reason, which is that here. Although, actually, I think maybe we. I think actually this can be removed because this is a bug which can happen even in a cluster with multiple replicas, and we should be thinking this. Okay, actually, okay, yeah, you see our pull request apparently passes all of our tests, which is good. Okay, workload. So workload is going to be like another big topic, probably a whole separate episode, maybe even more than one episode, because like, I mean, workload is like super hard. But like basically workload is a thing which generates random transfers. So I mean, there's like a lot of randomness already we've seen, like, randomness in the network, randomness in the storage, randomness in cluster configuration. But I mean, that is kind of like just environmental randomness. There is also the input. Like, you need to feed the cluster with reasonable inputs. And the inputs are called workload. They are also random. And yeah, we need thermal config there. Okay. And then we have probabilities for crashing replicas. Again, like with partitions, there is actually 4 numbers here. Transition in one direction, transition in another direction, and the length of stays in a single transition. Okay, pause. Okay, this is interesting. So we actually have like 2 kind of like modes for how the replica can crash. Crash is simple. So replica is completely, like the state of the replica is completely reset. It loses everything. And pause means that for a certain amount of time, a replica just doesn't participate. It is frozen. And at some later point, it gets unfrozen. And replica being paused models virtual machine migration. So normally processes don't pause. Normally processes exist and react to outside events, react to input output. But if you are running on a cloud infrastructure and your cloud infrastructure decides to migrate your virtual machine from one host to another, then the way it looks like from the outside is that a process freezes for like 5 minutes and then resumes. And yeah, this is what we are going to model as well. Okay, then we have, oh dear, we have our release infrastructure and how we do upgrades. Okay, do we have upgrades in our to-do? Because upgrades are, okay, we do have upgrades. Because upgrades are really cool. Okay, I will get to it at some point. Okay. And then we say, yeah, how many requests do we want, and what is the probability that at any given point in tick we do a request? Again, swarm testing. It can be as low as like 1%. We cannot do this like literal 0 because we do want to emit all the requests eventually. But it can be as high as like 100%. So we always run requests. Okay, and now we can see like that light mode, which I mentioned, which allows you to quickly detect big bugs. So you see, we start with our basic swarm options, and then we say, actually, no. We reduce the amount of nodes in the cluster. So typically, you will have like 6 replicas and up to 6 standbys, but actually, for light mode, let's say that we only have 3 replicas. And similarly, there is like option performance, which we use for performance testing. And there, the main thing is that we just set all the latencies to small predictable numbers. So yeah, so we say that like crash probability is 0, post probability is 0, etc., etc. Okay, so okay, I'm bad with my keyboard. These were the options. Yeah. And then remember that we have some options on the CLI. And if we do have some options on the CLI, then we fix them here. Okay, then we print out the most important options. Not all of them, but most important ones. So if you run VOPR, actually, let's look at the performance mode. I think, yeah, this is definitely not valid zip code. So this thing over here is exactly this thing. And you see that, yeah, performance, like most of probabilities are zeros, latencies are zeros, well, like delays like not zero, but small, etc., etc. And yeah, performance mode in the end also prints some stats about the number of messages sent. Okay. So now we initialize our simulator. Which we are not going to cover today. And then like the main body of the main like core of the simulator is like this loop, where we go and take simulator in a loop until we get requests to all the replies, replies to all the requests that we planned to issue. So once we did all the requests, and well, also once we did all the upgrades, we break. Otherwise, we continue looping. I think there is also... Okay, yeah. So, and like in this loop, like, you know, like there's a possibility that we should, there's a possibility that we can get stuck. So what we have here is that we have a limit for how long an individual request can take. So you see, we start with tick 0, and then we increment the tick. And every time simulator gets one more reply, we go and reset our ticks. And if we didn't reset our ticks, then we get into this else branch where, like, ultimately we are going to report simulator failure. Okay, and then we have liveness mode. Okay, so let me briefly explain what the liveness mode is. In general, in distributed systems, you are curious about two properties: safety and liveness. What is safety? Okay, let's say that, like, you know, we are building a distributed state machine. So safety means that at any given point in time, no two state machines disagree about what the state is. You violate safety if it so happens that there are like two machines and they think differently about like what was a particular operation. So I don't know, one machine thinks that like this operation is transfer money from Alice to Bob, but another state machine thinks that this operation is transfer from Bob to Alice. If you violate safety, yeah, that's pretty bad. But it is not the only failure mode you can have in a distributed system. Another failure mode is a failure of liveness. And this happens if one state machine thinks that there was a transfer from Alice to Bob, but the second state machine doesn't yet know that. So it doesn't tell you positively that, hey, I do not have this transfer. It rather says you, hey, I don't know whether it exists or not, and I'm going to wait until I learn more about the state of the cluster and get stuck there. So, like, you know, eventually you would expect every replica in the cluster to arrive at the same state, to fully sync up, to fully catch up. But if there is a bug in your implementation, then that might not happen. So that's why we kind of like split this loop into two parts. So this is safety mode. Here we check for safety violation. And at the end, here, we have a liveness mode, where we say, okay, so now let's see that we will not only not disagree, but actually converge to the same state. Actually, there is more I want to cover about liveness mode, because it is it's a bit tricky. It's not obvious that you need it, but you need it. But I think, yeah, I think that is going to be the next episode. I'm not sure. I'm actually not sure if I will be able to do it next Thursday because I will be traveling. But well, maybe I will. Other than that, okay. So let's call it today. It was unusually light episode. We just fixed one to do and then like looked mostly at CLI parsing options and that stuff, just so to slowly ease into VOPR, because I mean VOPR is a lot of code, so we are going to take it slowly. With that being said, please join me again next Thursday at 5 p.m. UTC live on Twitch. Or if you miss it for some reason, then all the recordings are always on YouTube, so you could always watch them there. Okay, folks, goodbye and see you in a week.